Welcome. Right now we are discussing our fourth chapter, line integrals. Today we are going to discuss the fourth module. In this we shall study fundamental theorems of calculus on line integrals. At first, we shall make a comparative study between Riemann integration and line integrals. Let us start with revising the definition of line integral. Let gamma from bounded closed interval AB to Rn be a piecewise smooth curve, capital A be an open set in Rn which contains the trace of the curve gamma, and f from A to Rn be a bounded function. The line integral of f along the curve gamma is denoted by line integral f d gamma and is defined by the following. Line integral f d gamma equals integral of the inner product f gamma t gamma dash t dt, where the limits of the integral are a and b, provided the integral exists even as an improper integral. We first note that in the above definition, the standard inner product Rn was denoted by angles as shown here. Also, we can relax the condition regarding the domain of f and consider f to be defined only on the trace of the curve gamma. Now, we discuss some differences between Riemann integral and line integral. First one, in case of Riemann integral, the domain of the integrand is a bounded closed interval. Now, using some properties of Riemann integral, we can extend this to an arbitrary compact set like union of finitely many disjoint bounded closed intervals. Now, in case of improper integral, this concept was extended to non-compact sets also. On the other hand, in case of line integrals, the integrand is defined on the trace of a piecewise smooth curve. The second point, in case of Riemann integral, the integrand is a bounded function, that is, it must be real valued. On the other hand, in case of line integral, the integrand is vector valued. If gamma is a curve with Rn, then Rn is the codomain of f and its range is a set in Rn lying in a bounded region. Now, we try to find an answer to the question, can Riemann integral be treated as a special case of line integral? That is, can we find some conditions under which from a line integral we can find a Riemann integral? So, we start considering a line integral f d gamma. We first observe that in such a case, the integrand f must be real valued. So, we take r instead of Rn, where n was arbitrary, as the codomain of f. Considering this situation, the curve gamma must be a curve in R. Now, we need our integrand look like ft. So, we must have gamma dash t equal to 1 for all possible t. If gamma t equal to t plus c for some constant c, then we find that inner product of f gamma t and gamma dash t equal to f of t plus c. So, we better take c equal to 0. Thus, gamma reduces to the identity map on the bounded closed interval AB. Thus, we have the following. Let gamma from bounded closed interval AB to itself be the identity map. Secondly, f be any bounded function defined on any superset of AB such that f is integrable over AB. Then, for every t in AB, we find that inner product f gamma t gamma dash t equals inner product f t and 1, that is product of f t and 1, which is nothing but f t. Consequently, line integral f d gamma equals integral a to b inner product f gamma t gamma dash t dt, which equals a to b f t dt, which is nothing but a Riemann integral. In single variable calculus, we studied fundamental theorems of calculus. Now we are going to study them for line integrals. Our strategy will be the following. First, we shall recall the result for single variable calculus. Then, we shall think whether we can make some alterations in that so the new one sets in the line integral format. If we find a meaningful statement, then we shall try to prove its validity. We start with the notion of path connectedness in Rn. Definition of a path connected set. A non-empty set A subset of Rn is said to be path connected if and only if every pair of distinct points in A can be joined by a curve gamma lying entirely in the set A. This means corresponding to each pair of distinct points PQ in A, there exist real numbers AB and a curve gamma from AB to Rn such that gamma A is P and gamma B is Q and trace of gamma is a subset of A. We know that every path connected set is connected but not conversely. A popular counter example is the topologist sine curve. But a connected set is path connected provided it is open. In the remaining part of this module, by a path connected set, we shall mean what we discussed above, and we shall add an extra condition that the curve gamma under condition is piecewise smooth. Now we are going to discuss second fundamental theorem of calculus of line integrals. First, we recall the second fundamental theorem of calculus of one variable. Actually, we are stating here a corollary of the said theorem. If a function capital F from bounded closed interval a b to R has continuous derivative over the corresponding open interval a b, we have integral a to b f dash u du equal to f b minus f a. Suppose we want to find a corresponding result provided it exists for a function of more than one variable, and instead of Riemann integral we consider line integral. Now let us look back at the result. If f from Rn to Rm is a vector field, then fb minus fa, that is the right hand side of the above result, is in Rm. But the left hand side of the above is a line integral which yields a real number. Thus, we must consider f to be a scalar field, that is our small m should be 1. So, now let f from A to R, where A is a non-empty open set in Rn. The advantage of considering A to be open lies in the fact that soon we shall consider differentiability of the function capital F over the set A. Moreover, our aim concerns with line integrals which deals with piecewise smooth curves. So, our further requirement that A should be path connected. As we have already assumed A is open, so we can consider A to be connected. As in the one variable case, we consider the continuity of f dash. Here we assume the continuity of gradient of f. With these adjustments, we have the following proposition. Theorem, second fundamental theorem of calculus of line integrals. Let capital A be an open connected set in Rn and capital F from A to Rn be a differentiable scalar field such that gradient of f is continuous over the set A. Let P and Q in A be arbitrarily chosen, and also let gamma be a piecewise smooth curve in the set capital A which joins the points P and Q. Then line integral from P to Q, inner product gradient f d gamma equals with fq minus fp. We give the proof here. Let gamma from AB to Rn be a curve such that gamma A equals to P and gamma B equals to Q. The existence of such a curve is assured by the path connectedness of the set A. Here we assume connectedness coupled with openness, which is equivalent to the required condition. At first, we assume that gamma is smooth. The piecewise smooth condition will be considered later. Now, line integral from P to Q grad f d gamma equals integral a to b inner product grad f gamma t with gamma dash t dt. Let us consider a real valued function capital G defined over the bounded closed interval ab by gt equals f gamma t for every t in ab. Since the curve gamma is smooth and the scalar field capital F is differentiable by chain rule, the function capital G is also differentiable. Also for every t, g dash t equals inner product of gradient f gamma t and gamma dash t. Moreover, by the given condition gamma is smooth and gradient f is continuous, so g dash is also. Consequently, line integral f to q gradient f d gamma equals with integral a to b g dash t dt. Here we use the second fundamental theorem of calculus and find its value as gb minus ga, which is nothing but f gamma b minus f gamma a, that is fq minus fp. Hence the result. Next, let gamma be a piecewise smooth curve. Then there exist finitely many points, say p1, p2, continued up to pn minus 1, all of them are in the set A, and finitely many smooth curves gamma 1, gamma 2 up to gamma n, such that gamma is the join of the curves gamma 1 plus gamma 2 up to gamma n. All of these lie in the set A, and for every I equal to 1 up to n, the curve gamma I joins the points pi minus 1 and pi, where we denote p0 equal to p and pn equal to q. Now we use the result we found for smooth curves, and we find line integral p to q gradient f d gamma equals with line integral for same function for the curve gamma 1 from p0 to p1 added with the same thing for the curve gamma 2 from p1 to p2, and continue this up to the nth curve from the points pn minus 1 to pn. Using the previous result, we find that its value is fp1 minus fp0 plus fp2 minus fp1 continued up to fpn minus fpn minus 1. Looking at this, we can easily find that only two terms will survive, that is fpn and fp0 with a negative sign. So we have line integral p to q gradient f d gamma finally equals with fq minus fp. This completes the proof. Now we consider the independence of path for a line integral. Let capital A be a open connected set in Rn. F from A to Rn be a continuous vector field. We choose 2 points P and Q in A. In the previous module, we have shown that it may so happen that line integral P to Q f d gamma assumes different values for different piecewise smooth curves gamma joining P and Q, such that the trace of gamma lies entirely within A. Thus, there exist vector fields F for which the value of the line integral depends not on the endpoints only, but on the path joining them also. In case the line integral P to Q f d gamma depends only on the endpoints P and Q and is independent of the curve gamma joining them, here we assume that gamma is piecewise smooth. We say that the line integral of f is independent of the path or path independent from P to Q. If further, for every pair of distinct points P and Q in A, the line integrals integral P to Q f d gamma is path independent, we say that the line integral of f is path independent over the set A. One remark at this point. From the second fundamental theorem of calculus for line integrals, we found that if capital A is an open connected set in Rn, f from A to R is a differentiable scalar field, that is, it admits a continuous gradient nabla f, then for every pair of distinct points P and Q in A and any piecewise smooth curve gamma joining the points P and Q, integral P to Q grad f d gamma equals Fq minus Fp. We must note here that P and Q may not be distinct. With this, we have the following corollary. Over an open connected set in Rn, the line integral of a continuous gradient is path connected. Note: let A be an open connected set in Rn and gamma from I to A be a piecewise smooth closed curve where I is an interval. Also let F be a scalar field such that grad f is continuous over the set A. We select an arbitrary point P which lies on gamma. Since the line integral is path independent, we have integral over grad f d gamma equals Fp minus Fp, which equals 0. Note that here we have considered gamma a closed curve. Hence, we conclude the following result. The line integral of a gradient scalar field defined and continuous over an open connected set over a piecewise smooth closed curve is always 0. However, the converse of the above statement is also true. We show it in the following result. If the line integral of a scalar field defined and continuous over an open connected set A in Rn over any piecewise smooth closed curve gamma lying entirely in the set A is always 0, then the scalar field is gradient. We start the proof. The proposition will be proved if we can show that for any PQ in A, the line integral of f from P to Q is path independent. Let alpha and beta be two piecewise smooth curves joining P and Q and lying entirely within A. Let minus beta denote the curve from Q to P travelling through the trace of beta with equal speed at corresponding points. Now we consider the join of the curves alpha and minus beta. Clearly, it is a closed curve. It starts from P and ends its journey at P. It is piecewise smooth. It lies entirely within A. We can consider it starts from P and ends at. To make it detailed, let alpha from AB to A and beta from CD to A be two curves satisfying alpha A equal to P equal to beta C and alpha B equal to Q equal to beta D. We define the join alpha plus minus beta by mu, which is a curve defined over the bounded closed interval A, B plus D minus C to A as follows. Mu t equals alpha t for every t in AB and equals beta B plus D minus t for every t in CD. Clearly, the line integral of f over the curve mu is well defined and also mu is a piecewise smooth closed curve. So, by proposition, integral f d mu must be 0. This implies integral f d alpha minus integral f d beta is 0. Hence, the result. Let us now recall the first fundamental theorem of calculus. Let f from AB to R be such that for every x in the bounded closed interval AB, f is integrable over the bounded closed interval A to x. Now, for every c in bounded closed interval AB, we define capital F suffix c from AB to R as fcx equals integral c to x fu du. Now, fc is well defined. It is differentiable at each point x in the open interval AB provided f is continuous at x. Moreover, for every such point x, we have capital Fc dash x equals with small f x. Now, if we consider small f is continuous over the bounded closed interval AB, then capital Fc is differentiable over the corresponding open interval AB and its derivative coincides with the function small f. Thus, this theorem tells us how to construct a function, say second, from a given function which we consider the first function. The first function must be continuous such that the first one coincides with the derivative of the second. Our present target is to construct a corresponding result in multivariable setting. So, we proceed step by step as follows. First, let capital A be an open set in Rn and F be a map defined over the set A. In the single variable version, the tool was indefinite integral, which we can replace here by line integral. So, first of all, we need a curve in Rn. For the inner product to be defined, F need to be a map from A to Rn, as we have started with a curve in Rn. So, F must be a vector field defined over the set A. Secondly, so our need is that given any two points P and Q in the set A, they should be joinable by a piecewise smooth curve. This is why we require path connectedness of the set A. As we already assumed openness of A, this requirement is met up by considering in addition connectedness of the set A. Third one, as the number of independent variables is likely to be more than 1, the derivative of f should be replaced by gradient of the function f. Fourth, let us select an arbitrary point A in A. Then for any point x in A, we can find the line integral a to x f d gamma. This defines a scalar field on the set capital A. As we have considered the point small a as the base point, we define capital F suffix a x equals line integral a to x f d gamma, where gamma is any piecewise smooth curve in the set capital A joining A and x. Now, the scalar field Fa must be well defined, and we defined Fa with the help of a line integral. So, we have to impose the condition that the line integral under consideration must be path independent. With this preparation and adjustments in mind, we state the following theorem and then prove it. Theorem: let capital A be a connected open set in Rn and F from A to Rn be a continuous vector field. We further assume that the line integral of f over the set capital A is path independent. We select small a in A arbitrary and then keep it fixed. We define capital F A x equals line integral a to x f d gamma, where gamma is a piecewise smooth curve in the set capital A joining A and x. Then the gradient of f a exists, and for each x in A, grad f a x equals f x. That is, the functions grad f a and small f are same. This means that for every I from 1 to n and for every x in A, del f a del x I x equals f I x, where small f, a vector field, has components f1, f2 up to fn. Proof: to prove the proposition, we have to justify two things. First, existence of grad f a over the set A. Number 2, equality of grad f a and small f at each point of the set A. We know that the partial derivative del f a del x I at x equals with f dash a x e I, vector derivative, where e I denotes the ith unit coordinate vector in Rn. This is why we first form a difference quotient fa x plus hy minus fa x divided by h. Now let x be an arbitrary point in A. Since A is open, the point x must be an interior point. So we can find a positive r dependent on x such that x lies in the open sphere Sxr and which is in the set A. Let y be any non-zero vector in Rn. We consider a real number h such that x plus hy lies in Sxr. That is, modulus h norm y must be less than r. We consider the difference quotient fa x plus hy minus fa x by h. So it equals 1 by h times line integral a to x plus hy f d gamma 2 subtracted line integral a to x f d gamma 1, which equals with 1 by h times line integral x to x plus hy f d gamma. Here we used the path independence of the line integrals and additive property of the line integral with respect to the path. Here, gamma 1 is any piecewise smooth curve joining A and x plus hy, gamma 2 any piecewise smooth curve joining A and x, and finally gamma any piecewise smooth curve joining x and x plus hy. As the point x plus hy lies within the open sphere Sxr and Sxr lies in the set A, the line integrals under consideration are path independent, and any open sphere in Rn is a convex set. We can consider gamma to be a straight line segment joining x and x plus hy. So let gamma from bounded closed interval 0 1 to Sxr be defined by gamma t equals x plus t hy for every t in 0 1. Putting here t equal to 0, we find that gamma 0 is nothing but x, and putting t equal to 1, we find that gamma 1 is nothing but x plus hy. Evidently, gamma is a smooth curve in Sxr joining the points x and x plus hy. Moreover, for every t in open interval 0 to 1, gamma dash t equal to hy. Then, fa x plus hy minus fa x by h equals 1 by h integral 0 to 1 inner product f gamma t gamma dash t dt. This equals 1 by h integral 0 to 1 inner product f x plus hty hy dt. So this is nothing but 1 by h times integral 0 to 1 inner product f x plus hty y h dt. Now we substitute u for ht. So du is nothing but h dt. So we have the given integral equals 1 by h times 0 to h inner product f of x plus uy y du. Now in the above we put y equal to ei, where ei denotes the ith unit coordinate vector. Then we find fa x plus hei minus fa x by h equals 1 by h integral 0 to h inner product f of x plus uei ei du. So this is 1 by h times 0 to h fi x plus uei du. Now let us consider the limit of the left hand side above and the right side of the above relation as h tends to 0. In case the limit exists, we can easily find the left hand side will yield del fa del xi at the point x. So we concentrate on the limit of the right hand side as h tends to 0. For every h lying in the open interval minus r to r, we define gh equal to integral 0 to h fi x plus uei du. Clearly, g0 is 0. As f is continuous, its component functions fi's are also continuous in A. By the first fundamental theorem of calculus, it follows that the function g is differentiable in the open interval minus r to r. Also, for every h in this open interval minus R2 R g dash h equals with fi x plus hei. In particular, putting h equal to 0, we have g dash 0 equal to fi x. On the other hand, g dash 0 equal to limit h tending to 0 gh minus g0 divided by h. So, this equals limit h tending to 0 1 by h integral 0 to h fi x plus uei du. So, this equals limit h tending to 0 fa x plus hei minus fa x by h. As the above limit exists, we find g dash 0 equals with fa dash xei equals del fa del xi x. Combining the results we have already found, we find that for every x in A, del fa del xi at x equals with fi x, that is grad fa equals with f. This completes the proof. One observation here, let A be a connected open set in Rn. If f from A to Rn be continuous and line integral of f is path independent in A, then by the above result it follows that f is gradient of some potential function defined over A. One remarks at this point, let B be any point in the set A different from A. We define another function fbx by line integral b to x fd gamma for every x in A. Here gamma is any piecewise smooth curve joining B and x. By the above result, we find gradient fb equals f. Thus, in a similar fashion, we can produce another scalar field fb from A to R whose gradient is the same vector field f. Moreover, fbx minus fax equals line integral b to x fd gamma 1 minus line integral a to x fd gamma 2, and that is integral a to b fd gamma, where gamma 1, gamma 2 and gamma are as usual. This shows that two such scalar fields differ only by a constant. So, we have discussed fundamental theorems of calculus for line integrals. With this module comes to an end.